Good afternoon, everybody. Thank you for the introduction. I'm going to talk about the reliability and the performance challenges of next generation smart power battery management systems for electric mobility, which is under supervision of Professor Crovetti and in collaboration with the ST Microelectronic company. In this talk, I'm going to talk briefly about what is BMS, and then we are going to focus on the vertical interface and talk about the vertical interface and how it is evaluated by different tests like DPI and BCI simulation. And then we investigate the failure mechanisms in the evaluation phase of the vertical interface, and then we conclude the talk. So, lithium-ion and lithium polymer electrochemical battery packs are becoming a to-go option for electrical and hybrid electrical vehicles. Because of their high energy density and high power capabilities, but they can be damaged and they can lead some life-threatening hazards like a fire, explosion due to the overcharging or over-discharging or overheating of the cells. So the presence of battery management system is essential to control, monitor, and report any errors in the performance of the batteries. So you can see here battery pack. In a battery pack, we have battery nodes. Each battery nodes contain, for example, 4 to 40 battery cells. And for each battery node, we need a BMS front-end IC to control its behavior and receive the data and everything, the information about the battery nodes. And these BMS front-end ICs are also communicating with each other and also with the control unit via the vertical interface transceivers. So the performance of the battery is important, and also the performance of the battery management system and how they are communicating with each other is also very important. Because the battery pack is in an environment with a lot of electromagnetic interface, which can produce some radio frequency disturbance, leading to some problems and leading to, again, some life-threatening dangers. So, according to the literature, the most critical electromagnetic interface susceptibility issues are related to the vertical interface, which is responsible for the communication and exchanging the data between the battery management system front-end ICs. So, what vertical interface is introduced. Now I'm going to talk about what I've done during my research. I proposed a WIF circuit, actually different versions of the WIF circuits to have a good performance and communication for the battery management systems. So here you can see the schematic view of these type of circuits. The WIF structures are comprised of a transmitter, electrostatic discharge protection circuit, which prevents the very high current pulses leading to damage to the circuit. A digital block at the end that converts the analog signal to the digital output bits. Capacitive coupling network, which capacitively, of course, couple the lines and the transceivers. And of course the receiver part, which contains comparators, transmission resistor in VIF number 2, and also a common mode voltage generator. So there are some differences between these two structures. The common mode input range for the comparators and also the threshold voltage of the comparators are different in two different structures. And the circuits for the protection over voltage, over current, and also EST protection are also different into two different VIF structures. And actually the VIF number 2 is somehow modified version of the VIF number 1. There are some other difference also in the structures, like how the resistors in parallel are replaced with series resistors to prevent the high voltage leading to high current flowing to the circuit. And that's it, yes. So the principle of the communication is actually the communication is a differential, capacitively isolated, bidirectional at 4 megabit per second. So the battery, the transceivers send and receive the data from the BMS ICs. The way of communication is also unique and different. Actually, the logic one is not like a simple high pulse, is a high pulse, a positive differential pulse followed by a negative one, and the logic 0 is in opposite way, the negative differential pulse followed by a positive one, and also there is an idle time between each transmission to guarantee that the transmission is done and the circuit is waiting for the next data. So how this structure is evaluated? There are many different standard tests. Two most famous one are DPI and BCI, which means direct power injection and bulk current injection, which simulate the RF disturbance in the environment, and we intentionally apply the power through these two different tests to the lines and to the circuit to see the performance of the system. So for example, the DPI is like injecting 1 microsecond RF power. The 1 microsecond comes from the fact that the working actually the frequency range for this test is from 1 megahertz to 1 gigahertz. So we apply at least 1 microsecond to have at least one period of the lowest frequency, which is 1 megahertz. Then at each frequency we change the initial phase of the disturbance to see if it affects the results, and then we consider the worst case of each of different phases in each frequency for the evaluation, and then we increase the power level to see if the communication is correct or not. And we continue this evaluation until we reach the maximum level, which is according to the standard 36 dBm, or we face a failure. If we face a failure, that point would be the immunity level of the system, of the circuit, at that frequency. And if we, of course, reach the maximum test level, the maximum is the immunity level. And at that frequency, the working is safe. So here you can see the results. You can see that there is a good correlation between the DPI and BCI simulation results. And of course, for the VIF number 2, we have better results. We have faced just some failures at low frequency, which is a problem, of course, and we should solve this problem. and we are going to solve this problem, definitely. So to find these failures, we should propose some benchmark parameters that based on these parameters we can say that the system is working well or not, we have a failure. So these benchmark parameters are introduced based on the differential signal at the input of the comparator. Which, why the comparator? The reason is that the comparator is the last part of the circuit before the digitalization. So if the comparator receive a proper differential signal, and of course if the comparator itself works properly, we can say that the communication is correct. So we introduce different benchmark parameters. The first one is delta int, which is the mean value of the comparator input differential signal exceeding the threshold voltage. So what is the threshold voltage? It is the voltage that if the comparator, the differential signal at the comparator reach this voltage, the comparator start toggling and could create the signal, the proper signal in the output. So the next benchmark parameter is that delta sig I defined, which is the difference between the positive threshold voltage and the maximum of the signal during a low pulse, and in the opposite way, the difference between the negative threshold voltage and the minimum of the signal during a high pulse. It means that the signal, the differential signal, should not exceed the opposite threshold voltage when it is in a high or in a low. Otherwise, we have a bad communication and we have two positive and negative signal during while we expect just one positive, for example. And the other parameter is about the idle phase, where we want the signal should be kept between the two threshold voltage. At this period, we don't want any data. It is just the time that the transceiver is waiting for the next data and is a guarantee that the communication is done for the previous bit. So based on these parameters, and as they are close to 0, we can say that the communication is close to a failure situation. So they should be positive in general. So we also consider the phase shifting for each frequency to see the effect of changing the phase of the disturbance for the results. And you can see here two examples of different RF signal initial phase for 5 MHz and 40 MHz. And it is quite obvious that for 5 MHz, which is the above graph, as we change the initial phase, the variation in the input of the differential signal, the differential input signal is more varying. So you can see also here the results of the benchmark parameters, and you can see a strong dependency of parameters in low frequency on the initial phase. And as we increase the frequency, the dependency is decreased above the 30 MHz. So in conclusion, I should say that firstly the BMS is very important for the battery packs, and the performance of the BMS is also very important to be safe enough to communicate and to send and receive the data correctly. Otherwise, we might have serious problems. I proposed this circuit. There are some probably imbalances in the structure and or some rectification phenomena happened in the ESC or over voltage over current protection circuits, leading to conversion of the common mode to differential mode interface. interference, and these conversions in presence of the electromagnetic interface can lead to a wrong communication. I should also mention that the comparator itself is working properly, because whenever the parameters are passed, the comparators operate in a way that the output digital bit is correctly generated. Further research also are being done, and I have some improvement in the results, but because they are not completed yet, I avoid to present them here. But yeah, that's it. Thank you for your attention.